Okay, so today we're going to talk about greedy algorithms. And this is, relatively speaking, one of the easy sessions of this course. We will see some of the simplest greedy algorithms today, but then we will use greedy ideas in all of the next modules of the course as well, especially when we get to graph algorithms and when we talk about minimum spanning trees. But for now, let's just do basic greedy algorithms. So an algorithm is greedy if it makes greedy choices, if it does something that intuitively seems to give us the best result. So does some sort of local optimization and hopes to get the best global answer. That's generally speaking what we call a greedy algorithm. I'll show you some examples of this today. And this is one of those 50-minute sessions, right? So I don't know if I can actually code them, but I hope that I can code the last one at least. Okay, so this is my first problem. And this is basically, let me just tell you what the input and the outputs are. So imagine that you have a tape. I don't know if any of you have ever seen a tape. Like, have you seen VHS tapes or cassette tapes at least? No. Okay, so tapes were the old school types of memory that we would use in computers. And basically, you couldn't just access a particular place on a tape. You had to scroll to that place, right? So the idea is that it's a kind of memory such that if you want to read the ICE entry in this memory, you have to scroll all the way from 0 to I. So reading from position I of the memory takes OI time. That's the idea. So imagine that I have n different files and I want to save them on a tape. Have you heard of mixtapes at least? Like when people use them to create playlists of songs? Okay, no, whatever. So let's say I have n files and each file has a size or a length. So file I has length li. And these lengths are given to you in the input. And you have a tape, you want to save these files on the tape so that you minimize the total cost of accessing them. Okay, I'm going to formalize this. So in the output, you're just going to print a permutation of all the files. So you print a permutation P. Let's call this, I don't know. So I show it like this. I say the first file is P1, the second file in the permutation is P2, so on to Pn of the files. Now, this is what you have to output. And of course, I want to optimize something. So I'm imagining that I would want to access each one of these files exactly once. So what is the cost of accessing a particular file? So what is the cost of accessing the ICE file? Basically, you have to start from the beginning of your tape and go all the way until you get to that file, and then you read that file too. So the cost of reading one file, let's say the file that is at position I of my permutation is this. It's just going to be the sum for every j from 1 to I of the length of pj, right? Now, I just realized that this is a little bit hard to write like that, so I'm just going to write it like this. So I mean the length, okay? So that's the cost of reading the ICE file. Basically, I have to start from the beginning, read every single file, scroll past every single file until I get to the ICE file and then read the ICE file as well. Now, my total cost would basically be the sum of all of these. So it would be the sum for every I from 1 to n of this same cost. Okay. So I want to minimize this total cost. basically I'm reading each one of my files once. I want to minimize the total cost that I'm spending to read everything. So that's my goal. Minimize total cost. So of course you have to output a permutation that gives me the smallest total cost. That's all. Okay. Now, where is the greedy aspect here? I'm just going to do the first thing that comes to my mind. Let's just sort the files based on their length, and let's put the shorter files first, right? Intuitively, that makes sense, because if I'm putting a file at position 1, it's contributing to the cost of every other file. If I put a file at position 2, it doesn't contribute to the cost of file 1, but it will contribute to the cost of files 2 and everything after that, and so on. So my first file will contribute to this total cost n times. My second file will contribute n minus 1 times, and so on. So generally speaking, I would prefer shorter files first, right? This is my intuition, and this is also my algorithm. By the way, today, all of our algorithms are just one line. So this is my algorithm. Just sort the files based on their lengths. And by this, I mean short files first. Now, why is this optimal? I actually kind of gave you the proof already, because I just said you can look how many times the length of every file is contributing to that sum. But here's a different proof. So this is the proof of correctness of my algorithm. And I'm going to give you this different proof because it basically gives you a paradigm that you can use pretty much for all of the greedy algorithms that we will see in this course. Look, I can give you a proof like I gave you before, which is just analyzing this particular problem. Or I can say something else. I can say, suppose someone gives me an optimal answer, right? I'm going to show that the answer that this algorithm finds is at least as good as this optimal answer that someone else gave me. And I'm going to show that this holds for any optimal answer that they give me. Now, very importantly, I'm not claiming that the optimal answer is unique. Imagine if all of my files have the same length, if all of them have length 1, every permutation is an optimal answer, right? So I'm not going to say that the answer that I'm finding is definitely better than every other answer. I'm just going to say, if you give me some other answer, some other optimal answer maybe, I would show that my answer is not worse than that. It's going to give me either the same cost or a better cost. Okay, so this is my proof of correctness. Suppose that someone has given me some permutation. So someone gives me a permutation, let's call it P prime. Okay, but my algorithm created P, which was the sorted permutation. Okay, I want to show that the cost of P is less than or equal to the cost of P prime. Okay, and by the way, when I say someone is giving me something, basically what I mean by that is universal quantification. So this holds for every P prime. I don't get to choose my P prime, someone else has chosen for me. Okay, so I have a permutation P prime that someone else has chosen and given to me. But let's say this P prime didn't put all the files in the order of their lengths. So there is some point in P prime where a longer file is put before a shorter file. And let's just assume that our files have different lengths as well, because I mean, you can do the corner cases where you have a lot of files of the same length, but let's just say the files have different lengths for now. So if P prime is not sorted, then there is definitely some index. Then there is some index I such that the length of the element that P prime put at position I is actually bigger than the length of the element that it put at position I plus 1. Okay. Now, my argument is very simple. Just take the two elements at positions I and I plus 1 and swap them. And I claim that this would either make it better or at least it wouldn't make it any worse. Okay. So this is what I'm going to say. I'm going to say, let's swap in this P prime. Let's swap the ice element and the I plus 1 element, I plus first element. Okay. Now, when I do this, if I look at the costs, what's going to happen to these costs? So for every element that was after index I plus 1, the cost has not changed, right? Because I have to start from the beginning, go through all the elements, go through I and I plus 1. It doesn't matter in which order I go through them. But if you consider, for example, an element I plus 2, I plus 3, so on, they all have the same cost as they had before, right? And I can say the same thing for all the elements before element I. Because for those files, for those elements, I didn't change anything because the cost of reading a file only depends on the files before it. And I'm not changing anything other than I and I plus 1. So the only costs that can change are the costs of file I plus 1 and file I. Now, what is the change in the cost of file I plus 1? So previously, the cost of file I plus 1 was the sum of every j from 1 to I plus 1 of the length of the j's file, right? Now I have swapped I and I plus 1. So now I plus 1 is coming before I. So my new cost is this same sum but now I don't have the lengths of the ice file. So minus, oops, I don't have enough space to write it. Let me move it. Okay, so it's the previous cost that I had minus the length of file number I, right? Because file number I was before I plus 1 before, but now I swapped them. So file number I is now after I plus 1. Now, what happens to file I? So this is what happened to file I plus 1. Let's look at what happens to file I. Well, previously, the cost was, again, the same formula, except that it only goes to I. Basically, the sum of the lengths of everything up until index I. Now, it's, again, the same sum, but now I have also put file I plus 1 before this. So it's the sum of j from 1 to I of the length of P prime j plus the length of file I plus 1. Okay. So if I look at my total cost decreased by the length of file I, and then it increased by the length of file I plus 1. Okay. But remember, the length of file I was bigger than the length of file I plus 1. So my total cost decreased. Okay. So I can do this step, and the total cost of my permutation will go down. Now, what happens if I just keep doing this step? I will basically do a sort, right? I'm basically every time finding two elements. This is bubble sort. I'm finding two elements next to each other that are not in order, and I'm swapping them. So, and every time that I'm swapping, my cost is going down. Now, this was in the case when I was saying that all the lengths are different. If the lengths are not different, I can also swap when the lengths are exactly equal, right? That would just not change the cost. But in any case, I can do a bunch of these swaps, and I can turn this permutation that someone else gave me, P prime, into the permutation that my algorithm outputs, which is the sorted permutation P. And at every step, I was only reducing the cost. I was never increasing the cost. So my output has to be optimal, because no matter what you give me, I will just decrease the cost until I get to my output. So my output has the smallest possible cost. Okay, that's it. So basically, we just showed that we want to do this like in a greedy manner. We just sort them based on their lengths, and it all works out. Now, let's look at a different situation. Let's say I have the same problem, but now I'm going to say that instead of having lengths, all of my files have the same unit length, right? So every file has length 1. But instead of accessing each file once, for every file, I have a frequency, and I know how many times I'm going to access it. Okay? So in the input, I'm going to say I have n files, all with the same length. But I also have fi, which is the number of times or the number of accesses that I want to make to file I. Okay. And again, I have to output the best possible permutation. So the permutation P that minimizes my costs. But now what's my total cost? Well, again, the cost of one access to one file is exactly the same as before. So it's just this sum. Okay, this is the cost of one access to file number I. But now I know that I'm going to have fi accesses, so I have to multiply this by fi. Right? That's the number of times I'm accessing file number I. And of course, I have to sum this over all of my files. So this is now my new total cost function. This is what I want to minimize. So you see all of my files have the same length now, but it's just that some of them are not going to be accessed very often. Maybe there is a file that I want to access only once, but some of them are going to be accessed much more often. Some files are going to be accessed thousands of times. Now, again, I think you can easily think of the optimal solution here. Put the files that you access most often at the beginning, right? And again, the argument is pretty much the same as before. If I put a file at the beginning, I'm going to pay very little cost to access it. But I want to assign this little cost to the files that I'm accessing over and over again. But if I'm paying a lot of cost to access a file, I prefer to access that file very rarely. So I prefer that my rare access files are put at the end. So this is my algorithm. Again, the algorithms are one line. It's just sort the files in decreasing order of frequency, in decreasing order of fi. Now, I want to prove that this algorithm is optimal. Now, my proof would be just like the previous case. Suppose someone else gives me a different permutation and claims that this other permutation is optimal. So someone else has the permutation P prime. My algorithm gave the permutation P, which basically sorted the files based on their frequency going down, right? I just have to argue that my permutation is better. Proof of correctness. I'm not going to write everything that I wrote for the last one. I'm just going to write the things that are different. So someone has given me P prime. Again, I find some position where this solution that someone else gave me is not doing the same thing as my solution. So I just find an index I such that the frequency of the item that this other permutation put at position I is actually less than the frequency that this other permutation put at position I plus 1. Right? And now again, I say the same thing. I say swap whatever you have at positions I and I plus 1. And your cost will go down. Okay? Now, I'm not going to write this again because the only difference is that instead of L, I have F. Right? So the idea is just the same as before. Swap P prime I and P prime I plus 1. Okay. So we've seen two variants already. We've seen a case where we had different lengths. And we've seen a case where we had different numbers of accesses or different frequencies of accessing each file. What if we have both of them? So this is finally the general case in which my input, again, consists of n files. Okay. And each file has a length. Let's show that by Li. And it also has a frequency, a number of accesses, Fi. And again, our goal or our output should be a permutation P that minimizes the total cost. Now, my total cost this time is going to consider both length and frequency, right? I mean, I already had this here, but here all the lengths were just 1, right? Yeah. So all of these lengths are basically 1 in this case. But if the lengths are not 1, then I get the other case. So I said they all have unit lengths. So the cost of accessing file number I would be this. I have to basically start from the beginning, from file 1 to I. And I have to read every one of them. So I have to do this, L of Pj, length of the file that is put at position J. But I have to do this Fi times, right? And then, of course, I'm summing over I from 1 to n. So this is my total cost now, which is the same as before, except that before all of my lengths were 1. Now I don't have that assumption. My lengths can be anything. Sorry. This is F of Pi, the i's file in the permutation. And here it's also the same thing. It's F of Pi. Okay. What would you do here? So for the previous cases, when I didn't have frequencies, when every file was accessed exactly once, I had unit frequency for every file. I just said that let's put the files that are shorter first, right? So I was basically sorting based on lengths. But then when it came to these frequencies, when I said that every file is accessed Fi times, but I didn't have different lengths, I said, let's put the files that are accessed more often first. So let's sort not based on Fi, but you can think of this as sorting based on 1 over Fi, right? That's how you can think of this. Because I'm sorting based on Fi in decreasing order. So it's like sorting based on 1 over Fi in increasing order. Okay. So what do you suggest I do here? I would just combine the two and I say, look at both lengths and the frequency, right? So this is my algorithm. I say, sort all the files based on what? Okay, so if they have the same frequency, if I have two files that are both appearing the same number of times, both are accessed the same number of times, which one do I want to go first? The one that has shorter lengths, right? So I can say, well, maybe let's sort based on the lengths, but then if I have two files that have the same lengths, I want the one that has higher frequency to go first. So maybe I can say sort based on lengths divided by frequency, Li divided by F. So again, this is just something intuitive that came to my mind. I'm saying, let's sort it like this. Okay. Just like before, I have to prove that this is actually correct. But thankfully, the proof is also very much like before. So let's do proof of correctness. I'm saying, suppose my algorithm creates some permutation P. So my algorithm creates P or outputs P. And someone claims that P prime is optimal. So someone is giving me another P prime. Let's say this is just another permutation. I want to show that the cost of P is less than or equal to the cost of P prime. Okay. Now, I do exactly the same thing as before. I say if P prime is not the same as P, there should be some index in which P prime is not putting the files in sorted order based on this new metric, right? So I say if P prime is not P, then there exists some index I such that in P prime, if I look at the lengths of P prime I divided by the frequency of P prime I, and if I look at the same thing for I plus 1, lengths of P prime I plus 1 divided by the frequency of P prime I plus 1, they're not in sorted order. So this one is bigger, right? Because otherwise P prime is just P. And again, I'm assuming that these ratios are different for all of my files. I will come back and fix my proof so that it also works when you have two elements that have exactly the same ratio. Okay. But if this is the case, now I'm going to do, again, exactly the same thing that I did before. I say, let's swap the i's and I plus first element in P prime. Let's swap P prime of I and P prime of I plus 1. And let's look at all the costs. Now, again, if you look at all the elements that were at index I plus 1 or after that, their cost did not change. I'm accessing them the same number of times, and they're in the same position that they were before. So the cost that I'm paying for them does not change. If you look at all the elements from index 1 to index I minus 1, again, I didn't change anything for them. I'm accessing them the same number of times, and they're at the same position, so nothing changes there as well. The only things that can change are the costs of indices I plus 1 and I. So I'm exactly in this situation. So let's do this. What happens to the file that P prime put at position I plus 1? I just realized that in this one, oh, I'm sorry, this one is supposed to also be P prime of I plus 1, and this one is supposed to be P prime of I. Okay. So what happens to the file that used to be at position I plus 1? I now swapped it, and it's now at position I. So before, the cost that I was paying to access this file was just the sum of j from 1 to I plus 1 of the length of the file that was at position j. But then, of course, this should be multiplied by the frequency of the file that was put at position I plus 1, right? Because this is the number of times that I was accessing this file, and this is the length that I have to go to access the file, right? Now, how did this change? I used to have file I before file I plus 1, but now I don't have it. So it just changed to the same sum, j from 1 to I plus 1. Actually, yeah, the length of pj times f of pi plus 1. I wanted to copy that, but I forgot. But now, how much should I subtract from it? Well, every time that I access this file, I don't have to go over the length of file I. So, by the way, these are all also p prime. So minus the length of the file p prime I times the number of times that I'm no longer going over it, f of p prime I plus 1. So I don't care about the part that remained the same. This is the change. So my cost for file I plus 1, when I moved it before file I, it decreased by this much. Okay. Now, I'm not going to write this sum again. I'm just going to say, look at the file that used to be at position I. How much is the increase in cost? So first of all, how many times am I accessing this file? It's just the f of this file. So f of pi. And every time that I'm accessing it, previously I didn't have to go over file I plus 1, but now I have to go over it. So my cost is increased by the number of times that I access file I times the length of file I plus 1. Okay. So if I look at my total cost, it decreased by this much for file I plus 1, and then it increased by this much for file I. Okay. So my total change in cost is just this minus this. So f of file I times length of file I plus 1 minus length of file I plus 1 times f of file, oops, what did I do? Minus length of file I times f of file I plus 1. Okay. I want to say this is negative. I want to say my cost went down. Right? But what do I know about these two files? I know that I chose these two files because they were not in order. Right? So this is what I know about the files. I know this. And from this, I want to say that this one is negative. Right? Isn't it obvious? Just multiply and move them around. Yeah, I don't like to do algebra, but it's obvious, right? Yeah, so this is the length of file I plus 1. I can multiply it by the frequency of file I. Here I have the length of file I can multiply by the frequency of file I plus 1. So I just multiply by the denominators and I move everything to one side, I get this. So basically every time that I'm swapping, my cost is going down. So the argument is exactly like before. my solution is optimal because I can take anyone else's solution and I can keep doing operations that would only decrease the cost and turn it into my solution. Now, here's the thing. This argument also works if they were equal, right? If these ratios were equal, I could also swap. The only difference is that the cost just doesn't change. So my correctness argument works even if I have repeated values in these ratios. I don't have to say that every file has a distinct ratio. Okay. Great. Let's see another one now. We are running out of time and this is not good. I want to go much faster than this. Let's say we want to do some class scheduling. So let's say that you want to sign up for some classes, and let's say that every class is only one session, and that session has a starting time and an end time. Okay. So my input is basically a bunch of intervals. My input is going to consist of n intervals, and each interval has a starting point, AI, and an end point, BI. Okay. So for example, maybe this is my input. Okay. And let's say that these are classes that you want to take, but unfortunately the ARO doesn't allow you to take classes that are at the same time. So if two of them intersect, you cannot take it. But let's say you really want to graduate, so you want to take as many courses as possible, right? So the output is going to be the maximum number of input segments, of input intervals that you can take, such that no two of them intersect. Okay, so what is the maximum number of non-intersecting segments or non-intersecting intervals? Now, okay. I'm not really asking for the solution itself. I'm just asking for the number, but actually you can have a greedy algorithm that gives you an optimal solution as well. That gives you just a set of non-intersecting intervals that is as big as possible, the largest possible. Now, again, I want to remind you that the answer here is not necessarily unique. So, for example, if you have two intervals and if they intersect, you have two possible answers. You can take this one or that. So the answer is not unique, but give me a greedy algorithm that outputs one of the optimal answers. So whenever the answer is not unique, we're fine with just finding one of the optimal solutions. Okay. Here's the algorithm I'm going to use. I'm going to sort everything based on their endpoints. And then I'm going to start greedily taking them, taking the classes. So I sort all the classes based on their endpoints. I look at the first class, I take it. I look at the second class. If it does not intersect with any of the classes that I have already taken, I take it. And then I continue like that. Okay, so this is my algorithm. Sort based on BI. And then say for every interval in this sorted list, if it does not intersect any of the intervals that I have already taken, then take it. If it does not intersect any of the previously taken intervals, take it. Now, I'm just writing it in English, but you can, of course, write it as pseudocode as well. So what would it look like here? So I'm first going to sort them based on their endpoint. And if I sort based on the endpoint, this one would be at index 0. This one would be at index 1. This is index 2. This is index 3. This is index 4, 5, and 6. Right? And then I'm going to just process my intervals in this order. I'm going to look at 0 and I'm asking, does this intersect anything that I have taken before? But I haven't taken anything before, so it doesn't. So I take 0. Then I look at 1, it intersects with 0, so I cannot take it. I look at 2, it intersects with 0, I cannot take it. I look at 3, it intersects with 0, I cannot take it. I look at 4, it doesn't intersect with anything that I have taken until this point, so I take 4. I look at 5, it intersects with 4, I cannot take it. I look at 6, it intersects with 4, I cannot take it. Let's say I have another one here. I look at 7, it doesn't intersect with anything that I have taken, so I take it. Now, this simple algorithm, in this case, gives me 3 intervals. And as you can see, it's possible to take 3 other intervals. For example, you could take 2, 4, and 7. Right? But you cannot take more than 3. 3 is actually optimal. Okay. Why is this optimal? Now, again, we have to argue that even though our algorithm is doing something simple, every time it's just taking something greedily, but at the end, it's going to give us the overall optimal answer. How can that be possible? Why is that true? Again, I'm going to do something similar. I'm going to say, suppose someone else gives me a different solution. Okay, so this is my proof of correctness. Let's say my algorithm outputs some set. It outputs S. It says take all the intervals in S. And someone else gives me T. And someone gives a different solution, T. And this is a solution as well, meaning that they don't intersect. I want to prove that the size of S is greater than or equal to the size of T. So I'm taking at least as many intervals as any other algorithm could take. Okay. Now, here's the thing. I just look at this first interval, interval 0, the one that ends the soonest. My algorithm is always taking this one into the solution, right? Now, I say, let's look at this other solution T. Does T also include this same interval? If it does, then it cannot include any of the intervals that intersect with 0. So it has all the limitations that my approach has. So generally speaking, if it does include 0, then what I know about T is that if T is optimal, then it cannot include any of the other segments that intersect with 0. And then from the rest of the segments, it's taking an optimal answer, right? So if I know somehow inductively, if I do an inductive argument and I say that my algorithm is optimal over n segments, and I'm doing induction on n, right? I can then prove this very easily. So let's say I'm doing an induction on n, which is the number of intervals. Don't forget the base case. If n is 1, the problem is trivial. My algorithm takes that one interval. You cannot take more than 1. Okay. Now, in any other case, someone else has given me a solution T. I ask, is this first segment that I put into my algorithm in T as well or not? If it is, then I know that, well, T, so I ask this, is this segment 0 in T? Now, there are two cases. If yes, then great. I can just use my induction hypothesis. I can say that T is taking segment 0, so it cannot take any of the segments that intersect with 0. So the size of T is going to be 1 plus the best possible answer over segments that do not intersect 0. Right? But that's great because the size of my solution is also the same. My solution is also taking 0. And then it says I ignore all the segments that are intersecting with 0. And then in the rest of it, it finds the optimal answer by induction hypothesis. Right? So in this case, I'm happy. The case that I'm not happy is when this other algorithm that found this other solution made a different choice. So it didn't take 0. Okay. For example, let's say it's outputting something like this. So it's outputting 247. It didn't take 0. What can I do in this case? Well, I can just ask what is the first interval based on the endpoint that this algorithm took. In this case, it's 2. I say kick 2 out, put 0 in. Right? Why does this always work? Because this other algorithm, of course, it's taking some intervals, so it's going to have a first interval based on the endpoints. So look at this endpoint. This endpoint has to be after the endpoint of 0. Right? Because by definition, 0 was the interval that had the smallest endpoint. Right? So if I replace this with this one, I cannot intersect anyone else because all the other answers, all the other intervals that were in T started after the end of 2. So of course, they also start after the end of 0. Right? So in this case, all I do is that I say take T and change it. Make a T prime that is T union with 0 minus the element in T that has the smallest b. So smallest element, or I called it segment, right? Segment with minimum endpoint in T. And so I'm just adding one interval and removing one interval, so the size is not changing. So if T was optimal, T prime is also optimal. But now for T prime, I can apply the previous case because T prime takes 0. So this shows that my algorithm is also optimal. Okay. Now, we ran out of time, but let's just talk about the runtimes really fast. So the first 3 greedy algorithms that we saw here, they were just doing sorting. And I mean, if you want to actually calculate the costs, you're also going over the array ones. But it's just sorting, so it's n log n. And then what is the runtime of this last one? Here I also have a sort. So that's going to take O n log n. But then I'm going to say just walk over this array in order and take whatever you can, right? Now, the problem is here. I ask, does this particular interval intersect any of the previous intervals that I have taken? And if I do that naively, if I just check this interval with everything else that I have taken before, it would take a lot of time, right? It would actually give me an O(n) squared algorithm. It will give me quadratic time. But I don't need to do that because every time when I'm taking an interval in, I can just remember what is the largest endpoint in all of the intervals that I have put in, right? And I always have to make sure that the starting point of this new interval that I want to put in is larger than the largest endpoint of all the intervals that I had taken before. So I just keep track of that one thing and I make sure that everything is. So again, just to go over this really fast. So I'm going to take 0 and I will remember what is the biggest endpoint. The biggest endpoint is here. So when I go to 1, I ask, is your starting point before the biggest endpoint? And it is. So it does intersect something. And then I ask the same thing for 2. Is your starting point before the biggest endpoint that I have? And again, the answer is yes. For 3, it's yes. For 4, the starting point is after here. So I can take 4. And now I update my biggest endpoint to the endpoint of 4. And then I continue like this. The starting point of 5 is before this. The starting point of 6 is before this. But the starting point of 7 is after this. So I update my biggest endpoint to the endpoint of 7. Okay, that's it. See you tomorrow.